Today, the topic has to do with discrete time processing of continuous time signals. We'll talk some about things like fractional delay and what are called digital differentiators. And it kind of all ties back to the sampling theorem and some aspects of that. And here's the list of things that by the time we're done with this topic, I hope that you really have under your belt. Several of these things we're definitely going to be specifically emphasizing in today's lecture. Depending on how the lecture goes and what the timing is and the clicker questions that we do along the way, at the end there may or may not be time to talk a little bit about a few of these bullets that are not explicitly part of the lecture. Okay, now I had this slide up before, which is basically to focus your thinking related to the Nyquist sampling theorem. I'll return to this probably at the end of the lecture. Let me just say at the outset that there is a lot of misunderstanding about what the Nyquist sampling theorem says and doesn't say. And let me also kind of comment a little bit of an editorial that with some of the recent literature in the field, you'll hear things, especially in press releases, about how someone has figured out how to beat the fundamental Nyquist limit. Anybody who says that just doesn't understand what the sampling theorem is and what it isn't, and would not do very well on this set of clicker questions. So I'm very eager for you to understand kind of what this is all about at some point over the next couple of weeks. But what we're going to be focusing on today is this basic system. It has to do with what is generically referred to as discrete time processing of continuous time signals, where we have a continuous time signal, we somehow convert it to a discrete time signal, process in discrete time, and then convert back to a continuous time signal. It's a discrete time implementation of a continuous time system. Now, that's not the only reason why you would think of processing discrete time signals. There are lots of reasons going back to a lot of the history in what's called time series analysis, where you inherently have discrete time data and you want to do something to that discrete time data. And that discrete time data may not have come from sampling a continuous time signal. Now, also, when you look at this, of course, there's a continuous time input, there's a continuous time output, and so if this happened to be a DSP chip in here, but I had buried all of this in epoxy, then from your point of view, you would not know whether it was implemented as an analog system or whether it happened to be implemented as a discrete time system, since it's continuous time input, continuous time output. Something to understand carefully, and understanding it is not a very complicated thing, but it is important to have it clear in your mind that this overall system, as I've drawn it here, first of all, C to D is an abstraction. And I'll define it specifically in a minute, but it's an abstraction. This is an abstraction. And this overall system from continuous time to continuous time is linear as long as this system is linear in the discrete time domain. The continuous time system from here to here is not necessarily time invariant. And it's easy enough to kind of see that that's the case, because think about putting in a little narrow signal in time, and what's happening here is some kind of a sampling process, and if the sampling process happens to happen when the signal isn't there, you're going to get one output. And if it happens to happen when the signal is there, you're going to get another output. So in general, this is not a time invariant system, but it is a linear system. Okay, so step number one is to just define what the C to D and D to C are. And very specifically, if I have x sub c of t and I have the C to D and some parameter capital T, and the output of that is a discrete time signal, the definition of this box is that x of n is x sub c of n capital T. And so what you could say is, well, these are just equally spaced samples of x sub c of t, and that's correct. But there's no implication in this box as to how the box is implemented. And very specifically, the box does not include any amplitude quantization. So it's not an A to D converter in that sense. It's a C to D converter. Now, you can think of this as taking x sub c of t and sampling with an impulse train. And so the impulse train you could write mathematically as continuous time impulses. And then you could, let's say, label the output of this, which is a sampler, as x sub s of t. And then there's another kind of magic box. There's another magic box that you could label as impulses to samples, and that would give you x of n. And this would do the same thing as this. And in fact, this is not a bad way of thinking about it from the point of view of mathematically analyzing how, for example, the Fourier transform here relates to the Fourier transform here. But it's important to keep in mind that when I draw this box, the implication is not that we're sampling. Certainly the implication is not that we're quantizing. It's going through a process of, however we do it, getting equally spaced samples of this continuous time signal. Okay, so I think everybody here probably knows from their signals and systems background how the Fourier transform of this is related to the Fourier transform of this. If x sub c of t has a Fourier transform which is x sub c of j omega, then x sub s of t has a Fourier transform x sub s of j omega, where x sub s of j omega is equal to the scale factor of 1 over t. And you probably want to remind yourself at some point as to why the 1 over t is here. It has to do with what the Fourier transform of an impulse train is. And then what you have is a sum of x sub c of j omega minus 2 pi k over capital T. And so the Fourier transform here, as I'm sure you know from your signals and systems background, is this Fourier transform periodically replicated with a scale factor periodically replicated by integer multiples of the sampling frequency, which is 2 pi over capital T. All relatively standard stuff. So then if you kind of look at this pictorially. For example, if this is the continuous time Fourier transform, this is the Fourier transform of the impulse train. There's the scaling on it, which you may or may not remember exactly. You convolve this with this, you get replications. And if the highest frequency here is less than the sampling frequency minus that highest frequency, then these replications don't overlap. Otherwise, they do overlap. And if they do overlap, that's called what? Aliasing. So again, relatively standard stuff. And from this picture, it's pretty straightforward to argue that I can get this back from this picture by just extracting this baseband replication, i.e. by ideal low-pass filtering, whereas I can't if these replications overlap. And so, again, that's pretty standard signals and systems discussion. Okay, now if we go back to this picture, and what we want to relate next is what the Fourier transform of this is to the Fourier transform of this. And algebraically, that's also pretty straightforward because, let's see, if we look at x sub s of j omega, so that is the usual Fourier transform integral that I would do, but that Fourier transform integral corresponds to taking the Fourier transform of x sub s of t, and let's see, x sub s of t is the sum of x sub c of n capital T delta of t minus n capital T. So if I take the Fourier transform of this, it's pretty easy to do. So let me write that up here. I'll have the sum on k x sub c of n capital T, and then the Fourier transform of this delayed impulse is just e to the minus j capital omega n capital T. So that's what this Fourier transform is. Well, let me write that just a little differently, because we know that with the C to D converter, x of n and x of c of n capital T are the same thing. So this is the sum of x of n e to the minus j capital omega n capital T. On the other hand, if we ask what is x of e to the j omega, where what I mean by this is the Fourier transform of x of n, then that's just equal to the sum. And I need to keep my notation consistent, so I either can use k or n, but I can only use one of them. So this also I'll write as n. And this is the sum on n of x of n e to the minus j omega n. So somewhat of a problem I often find, and it's why I don't like to spend a lot of time going through a bunch of math and algebra on the board, is very typically what happens is the class goes into a mode of copying down what I'm writing and not focusing on what it says. So what I want you to focus on is what it says, and this compared with this tells you how x of e to the j omega is related to x sub s of j omega, what it says is that's equal to x sub s of j omega, but with a change of variables where omega capital T is equal to little omega, or capital Omega is replaced by little omega over capital T. So the mental picture that I'd like you to have in your mind is that as we go through the C to D converter, there are two things that happen in the transform domain. So one has to do with periodic replication, and then the other has to do with a normalization of the frequency axis. And in fact, if you look at this transformation or this scaling, it's a normalization. And the way I personally always remember what that normalization is it says that we're normalizing the frequency axis so that the sampling frequency, when we're in the discrete time domain, gets normalized to what frequency? It gets normalized to 2 pi. So what I kind of carry around in my head is that 2 pi is the normalization of the sampling frequency. And there's another kind of simple way to carry that around in your head. In some sense, you could say it's almost obvious that that's the case, because what's happening in the C to D, if we look at the second picture down, is if you think of it as sampling with an impulse train to capture the sample values, the spacing between those impulses is capital T. Once we convert it to a sequence, the spacing between the sample values is normalized out to 1. So we're basically dividing the time axis by capital T to normalize from spacing of capital T to spacing of 1. So what that means is we do the reciprocal normalization in the frequency domain, and that's where we end up with the sampling frequency getting normalized to 2 pi. So that's just kind of a way to think about it and carry it around in your head.